So here we are now, almost done with the course, right into chapter 9 of 10. So we're really going to start to pull things together here and think more critically and hopefully apply all those chemistry skills you've been acquiring this semester. So chapter 9 is going to address reaction rates and chemical equilibrium, two very important concepts. Reaction rates talk about how fast reactions happen. Up until now, we've just sort of said this reaction will occur, and we haven't given any consideration as to whether it's a fast reaction or a slow reaction or an in-between reaction. So this particular section of chapter 9 here is where we'll focus on those rates of reactions for a number of select reaction types. Before we can consider how fast a reaction occurs, first we have to understand why chemical reactions happen in the first place. And we've talked a little bit about this earlier in the semester, but now that you're really well versed in chemistry, let's take a moment to just understand the factors that allow for chemical reaction. First of all, chemical reaction involves two or more species coming together, or one or more species decomposing in order to have a new and different product or products formed. So that happens when we get collisions between reactant molecules that have sufficient energy to break the existing bonds. It always takes energy to break bonds. It always gives off energy to make bonds. We're just looking for when that's going to be favorable. Not only do they have to collide with sufficient energy, they also have to collide with the proper orientation. There may be a reactive end of the molecule and an unreactive end of the molecule, and in order to get a successful reaction, we need those active portions of the molecules to collide. Finally, the bonds broken between the reactants, in this case we're showing nitrogen and oxygen reacting, they are broken. That requires the input of energy, actually a lot of energy for this reaction, which is why air, which is mostly nitrogen and oxygen, doesn't just react on its own. It requires quite a bit of energy, something like a lightning strike in nature or some artificial input of energy in the chemistry lab to cause this to happen, because we need to, again, overcome that barrier and break those existing bonds, which requires the input of energy, before we can make the new bonds, in this case NO bonds, that will release energy as they form. All right, so if that's what's required for a successful reaction to take place, well then a chemical reaction won't take place if either the collisions between the reactant molecules don't have sufficient energy to break those existing bonds, or if they're just not in the proper orientation. They're not properly aligned for reaction. So in the top case, we see those same nitrogen and oxygen molecules coming together, colliding, but not with enough energy to break those existing bonds, and therefore we can't make new bonds. So we just end up right back where we started with the nitrogen and oxygen molecules as they were. Likewise, if they hit in the wrong orientation, and this is probably a bad example for that because there may be more successful orientations than what we show here, but in this case, if they hit in the wrong way, they will not react, even if they have sufficient energy. Even if they hit with enough energy to overcome that activation barrier, if the orientation factor is wrong, you will not get a successful reaction, and you'll just have the two species sort of recoil, and you stay with your starting materials. So those are a couple of big causes for a reaction to fail to occur. Just because we can write a reaction on paper doesn't mean that we can do it in the lab unless we get the conditions just right and unless the energies are just right. Now that you have those pictures in your head, let's take a look at activation energy. So here's a graph showing us, in the case of the nitrogen and oxygen, they are pretty low energy to start. So they're very stable. Those bonds are quite stable. And we know that because as we move forward for the progress of reaction, or reaction coordinate as it's sometimes called, along the x, we have energy along the y. And we notice that in order to get reaction to occur, we have a big energy barrier to overcome. And then our products are actually higher energy than our starting materials. So nitrogen and oxygen are quite stable molecules. In order to get them to do any chemistry, we've got to put in lots of energy to break those existing bonds, and in many cases, like we see here, the products are actually higher in energy than the starting materials. So that just indicates that we had really, really stable things to start with, and we had to put in a lot of outside energy in order to break those bonds. Again, activation energy is that minimum required to start breaking those existing bonds in order order to form new bonds. So activation energy can be quite high, as we see in this case for nitrogen and oxygen, two stable molecules. It can also be pretty low for something like an explosive, something that's really ready to react and has just a little barrier to overcome. So activation energy varies. Sometimes the reactants are lower energy than the products, sometimes the products are lower energy than the reactants, but regardless of that, the activation energy is at least a small amount of energy that needs to be overcome in order to get reaction happening by breaking those existing bonds. And sometimes, like we see here, that activation barrier can be quite large. So if we're now able to say that we're going to have a successful reaction because we're going to have enough energy and we're going to have the proper orientation at least some of the time, then we can start to talk about the rate of reaction. And the rate's determined by measuring how much of that reactant is used up or how much of the product is formed over a certain period of time. So we see here in the middle of the slide, rate of reaction equals change in concentration over change in time. And by convention, usually we're following the disappearance of reactants. That's our usual way that we do it, although of course we could also follow the formation of products. Rate of reaction is affected by a number of factors, most importantly temperature changes. Every 10 degrees Celsius temperature change roughly doubles the rate of most reactions. Again, that's a rule of thumb. It's not without exceptions, but that just gives you an indication of how powerful a factor temperature change can be in a reaction rate. We also have changes in concentrations themselves. If we have more reactant, then we're going to have more successful collisions because we're just going to have more collisions, period, and some percent of those collisions will be successful. If we had less reactant, if we had a lower concentration of the reactants, then they're less likely to hit each other. They're less likely to hit each other with sufficient energy. They're less likely to hit each other with the right orientation, and so that slows down the reaction. And finally, the presence of a catalyst, which is a species that usually just helps with that orientation factor. In the case of the types of catalysts that we'll investigate in 142, if you stick with me for that second semester of GOB, General Organic and Biological Chemistry, you'll see that a lot of the biocatalysts, the enzymes, they're just getting that orientation factor right. They're holding it in just the right way to react so that you've got much greater likelihood of success because now all you need is sufficient energy. The orientation factor is pretty well fixed. So those are three very important things that affect the rate of reaction. And again, those are indications of how we can increase or decrease the rate of reaction. Sometimes we're looking to increase the rate of reaction, right? If we're talking about making things in the synthetic chemistry lab or for industry, we want to be able to do that quickly and efficiently. Other times we want to slow reaction rates. That's why you probably put your food in the refrigerator or freezer if you're not going to be able to get at it right away. That slows those reactions that bacteria cause that would result in food spoiling. By lowering temperature, we can decrease that reaction rate. So sometimes we want to speed things up, sometimes we want to slow things down, and these are the main ways we can do those things. All right, so just to explain again, at higher temperatures, the reason we tend to see increase in reaction rate is that we increase the kinetic energy, the average kinetic energy. That's what temperature is a measure of. So if the average kinetic energy gives more energy to the average molecule, then we're going to get faster moving molecules, which result in more collisions, and therefore more colliding molecules will have sufficient energy to react and form products. We'll still have unsuccessful collisions because we'll still probably have the orientation not quite right, but we'll certainly have more collisions overall, and then as a percent, more successful collisions. And here, again, as I just mentioned, we refrigerate perishable foods to slow down those reactions that would ordinarily cause spoilage. If we look at that second factor, increasing the concentration of reactants, well, that's going to increase the number of collisions and therefore increase the number of successful collisions. We'll still have the same rough percent. If we hold temperature constant, we'll still have the same rough percentage of successful and unsuccessful collisions because of energy or orientation. But here, since we have more collisions, and actually if we've increased the concentration, we hope that we would see more collisions because there's more reactants present, we would expect an increase in reaction rate just because we have more collisions occurring and statistically more successful collisions as a result. And looking at that third feature, the presence of a catalyst speeds up the rate of reaction. we can see it doing that here graphically by lowering the activation energy. You don't need as much energy to overcome those existing bonds when you have a catalyst present. And a catalyst can participate in the reaction. What makes it a catalyst instead of a plain old reactant is that it's not used up. So it may be consumed at one step and then produced again at a later step. So as long as you see it starting and ending the reaction in the same form, then it's a catalyst rather than a reactant or a product. So there we have it. Catalysts, like I said, will be very important for biological chemistry if you stick around for the second half of this course. All right, so how's that for a fast introduction to chemical reaction rates? So let's pause here for a learning check. In this learning check, you're going to state the effect of each change on the rate of reaction as either increases, decreases, or no change on that rate. So go ahead, read those 5 features, jot down whether you think it will increase the reaction rate, decrease the rate, or have no impact on the rate whatsoever. Pause the video here while you make those determinations and start back up when you're ready to check your work. Okay, so in the first case, if we're increasing temperature, as we said, that's going to increase the average kinetic energy, which means the particles are moving faster and with more energy, and we're going to have more successful collisions as a result, so that should increase the rate of reaction. Number 2, removing some of the reactants. Well, if there's fewer reactants there, then there's going to be fewer successful collisions because there's just plain going to be fewer collisions to begin with, and therefore we're going to decrease the reaction rate. Number 3, adding a catalyst. As we said, that lowers the activation energy, and therefore more particles will have enough energy for successful collisions, so will speed up or increase the reaction rate. Number 4, placing the reaction flask in ice. If we're assuming it was room temperature and we've moved it down to ice water temperature, then that's going to slow the particle movement and lower their average kinetic energy, and therefore decrease the number of collisions and therefore the number of successful collisions. And finally, increasing the concentration of a reactant will have the opposite effect of number 2, where we remove some reactant. If we increase the amount of reactant, then we're going to have more collisions and therefore statistically speaking more successful collisions as a result, so the reaction rate increases. Hopefully those went well and you were able to identify those all correctly in pretty short order. If that's not the case, let's follow up with another learning check here just to make sure that things are making sense. All right, so in this learning check, you're asked to indicate the effect of each factor listed on the rate of the following reaction as increases, decreases, or does not change. So the reaction we're following is 2 moles of carbon monoxide gas reacting with 1 mole of oxygen gas to form 2 moles of carbon dioxide gas as the product. So you'll look at those 4 things and just like we did in the previous learning check, decide whether that's going to increase the rate, decrease the rate, or not have any impact on the rate of reaction. Please pause the video here and start back up when you're ready to check your work. All right, and here we see, so A, if we're raising the temperature, that should increase the rate of reaction, right? We said that that would increase the average kinetic energy, so the particles are moving faster and with greater energy, so you'll have more successful collisions because you'll have more collisions, and you'll have more collisions with sufficient energy to cause reaction. B here, removing some oxygen, that's removing a reactant, so that's going to decrease the rate of reaction because then we'll have fewer collisions and therefore fewer successful collisions. For C, adding a catalyst, that's going to lower the activation barrier, and then you'll have more particles that meet that energy requirement, and therefore you'll increase the rate of reaction. And finally, D, lowering the temperature, well, that's going to slow down the particles. It's also going to lower their kinetic energy on average, and therefore you're going to have fewer collisions and fewer collisions with sufficient energy to react, so that will decrease the rate of reaction. So hopefully if you struggled at all with the first learning check, this one was a little better for you. If not, if you're still not quite sure what's going on here with chemical reaction rates, please do reach out to me. Try some additional problems first. There's lots in the chapter itself and a couple in the homework set, but certainly reach out to me if you would like some more guidance. All right, other than that, we will see you for the next part of Chapter 9.